Okay, discrete random variables. Earlier, in an earlier module, we had talked about the idea of a random variable, a discrete random variable, and we're going to combine the notion of a random variable with probability, okay? And that's going to allow us to look at what's called a probability distribution. And so we want to consider these variables something, in this case, a random variable is a quantity or a quantitative variable whose value depends on chance, and we've seen that before. It's discrete if the possible values form a finite or countably infinite set of values. Okay, and so here's an example of a discrete random variable: the number of siblings a person has, the sum of the dice when a pair of dice are rolled, the weight of a newborn baby, the lifetime of a battery. These two are continuous variables, and these first two are discrete random variable examples. Well, we're going to focus on discrete random variables and also look at how probability plays a role in this situation. So let's look at this through the lens of an example. Consider flipping a balanced dime. Balanced means that the chance of head and tails is the same. And let x be the number of heads observed in those three flips. X is clearly discrete, right? X can take on 0, 1, 2, or 3. Okay, and so I want to, excuse me, I want to use a classical approach to come up with what's called the probability distribution. And to give some notation here, I'm going to have little x and capital X. Okay. Now for a while we'll make a special designation. The capital X is the random variable, and the little x is an arbitrary realization. Of the random variable x, capital X. So notation wise, the little x has this barb on top, and the capital X is just a standard capital X there. Okay, now what I'm going to do here is I'm going to write out the possible values for x. Again, x is the number of heads out of 3 flips. I could see 0 heads, I could see 1 head, I could see 2, or I could see 3. What are their associated probabilities? Okay, what's the chance that I would see 0 heads out of 3 flips? Well, let me come back to some basics here. The sample space for this experiment will look something like this. I could toss 3 heads in a row. I could toss a head, head, then a tail. I could toss a head, tail, head, or a tail, head, head. I could toss, let's see here, head, tail, 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 head, tail, 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 head, and then lastly I could toss 3 tails. Okay, so there's 3 outcomes in there, and those outcomes are equally likely. And so if I use the classical interpretation approach, which is reasonable here, the chance that x is 0, the probability that x is 0, okay, that means I'm going to see 0 heads. How many ways can that happen? Well, only in this outcome, the 3 T's there, can I see, there, we'll go ahead and highlight that, 0 tails. All right, so there's 1 out of 8 ways for that to occur. All right, 1 out of 8. Now what about for x to be 1? What's the probability that would occur? Well, how many ways can we have x be 1, or how many ways can we have 1 head? Well, that occurs in these 3 ways. So this probability is 3 out of 8. And then if you look further, you see this probability is 3/8. And then lastly, this probability is 1/8. Okay, this is called the probability distribution. It gives me the possible values of the random variable with their associated probabilities. It uses this name distribution. We've seen this before in terms of a frequency distribution. The idea is kind of the same, except we're dealing with a random variable and not a data set. But we are looking at a listing between the possible values of the variable and their associated probabilities. Now we can plot this thing on what's called a probability histogram. Look like this. I could have a 0, a 1, a 2, or a 3 for x, and the vertical, that would be my horizontal scale there. The vertical scale would be the probability that capital X equals little x, and it of course would start at 0 but go up to 1/8, let's say 2/8, and then 3/8 there. Okay. The probability histogram, the probability that x equals 0 is going to have a height of 1/8 there. And so I'm going to draw a bar that represents that. When x is 1, the associated probability is 3/8. When x is 2, the associated probability is 3/8. And when x is 3, the associated probability is 1/8. Now when we look at a probability distribution, or a picture of it called the probability histogram in the discrete setting, we can talk about this. You know, this graph looks symmetric, and it does, and it has a balance point right here, and that has a particular meaning in probability theory. But for us, I just wanted to set the stage. Okay, we're dealing with this thing called a discrete random variable. A few properties of the discrete random variable are as follows. The probability associated with each value of x lies between 0 and 1. All right, and that makes sense if you look at our example. Each of these probabilities here is between 0 and 1. Okay. Next property is that the sum of all the probabilities for all values of x is 1. So if you added up these probabilities again, you would get 1. And then thirdly here, the probabilities for a discrete variable are additive. What that means is the chance of x being 1 or 2 is equal to the chance of x plus the chance of 2. Okay, so it has that nice what we think about probabilities breaking over an or statement, or the union. Okay, so this is just a short introduction to discrete random variables. We have a discrete variable, a probability distribution, and a probability histogram. The one thing I do want to make clear is that this distribution, or the values in here, are the associated probabilities for point values of x, and we'll see it's slightly different under the continuous case. But from here we're going to move to from this short introduction to a more lengthy discussion on the binomial distribution, which is a particular discrete distribution.